All right, okay, listen up. So let's get started. So firstly, thank you for those who come into the consultation for the assignment. I think it's really important that you actually do. So there are two. By the way, if you don't mind me sharing your own findings with the rest of the class, which I found if it's useful. So the first thing that I wanted to tell people is that just in case you do not know any of the software that's used for your what do you call it? Your image detection. So if you take an image of your checkerboard and you wanted to know the corners of the image, so you can use, there's a program actually allow you to do that. It's called PixPy. And thanks for that student for asking that question. And she actually found that software. So this is a very useful information for people. But I'd imagine there are other softwares out there. There's another question that's asked about how do you obtain the two equations to compute your homography? Here you go. So these are the, sort of just went back and very quickly type. Well, I don't have time to type them out. So here you go. So one configuration. Okay, one configuration. You get one. You will have two equations. So basically, this is your M, which is the configuration, and this is your image. Hopefully, I actually put them in the right order. And here is your homography. And then because you need to normalize it to make this guy to become 1. So you can just normalize it to become 1. And you have to solve it. So I think maybe in the class I was telling you that this has to be 1. But that's really up to you. You can actually make this thing equal to having all your 9 degrees of freedom. But the important thing is to say that you will, yeah, someone close the door for me, thank you. The important thing is that you're actually gonna get 2 equations out of it. So you just, that times the U, you get 1 equation and you have another equation, okay? And then you will actually put all your H. Essentially, these are your variables. You will put them in here, all right? And you have your system A, and you need to solve H in your node space. I'm sure that you can actually do that. It's quite easy. Okay, so that's all I wanted to say about the this homography. I actually did not include that in the lecture notes because it's homework. Homework, I expect a lot of people to figure out those details by yourself rather than follow exactly what the note says. Here's just one way of doing that. You can actually solve it using multiple ways. But the important thing I do wanted to stress, please do have more equations than the unknowns. Don't use 4 points exactly, okay? All right, use least squared as much as you can. So yeah, I will include that I will actually type this out in the lecture notes. So you will see an updated lecture notes just then. So thank you for those of you who show up to the consultation. And if you don't, would you like to have another consultation regarding the homework? So maybe it will be sometime. So I just show of hands. So how about Wednesday, kind of 5 p.m. Is that going to work for everyone? Or maybe we should have like a little bit later, like let's say Thursday. This is a kind of closer to your deadline, and you probably will have a lot more time allocated to do your homework. So yeah, just so it will be around about 5 p.m. Okay, so I will send people an announcement. So please do come in and ask me questions, like what I'm going to be doing today, and I will actually show up. I will get a group of you come come together, and also that kind of saves me time as well to actually show my answer to a group of you rather than show you individually. So cool. I will just type them out and I'll include them in the lecture notes. Which, by the way, it wasn't meant to be initially. I was really trying to get you to figure out for your part of your homework. Okay, so no more questions. Is there any question from last week? So what did we study last week? Nothing? What did we talk about last week? Yes, so what is RKHS? I do have a much nicer way of explaining, which I thought about maybe it's appropriate for undergrad student. So just think about this, right? Just think about this. Think about like a Gaussian distribution, where you have the exactly the same variance. Now, if you think about a Gaussian distribution and removing the normalization constant, so you have, say, a Gaussian distribution that looks like this, mu, well, a Gaussian. And you have your mu1, okay, and your, that. And because this Gaussian would have mu1 as its mean, but I'm gonna get rid of the normalization constant. So it will look something like this, right? exp minus half and x minus mu1. And just try to make it even. Oh, I'll include them in there. All right. So I have this Gaussian distribution that looks like this, okay? And it's mu1 as its mean. And I have another Gaussian distribution. Okay. Then essentially I got two functions. And as you have seen it last week, this is essentially the radial bumper kernel, right? So if you get rid of this, like half here, it doesn't matter. So, and I wanted to measure the distance between the two. I want to measure, the distance between this distribution and another distribution. Maybe instead of distance, I wanted to say, I want to measure the similarities between this and this, okay? I just wanted to measure that. As you know, there are multiple ways of how you can measure the similarities between two distributions. I mean, in this case, we're really not treating it as a distribution. We are treating it as a function. You just wanted to measure the similarity between these two. And I wanted to say that, now this is what magically happens. The way in measure the similarity between these two functions, okay? I should also use this function in this form, okay? So, so I'm gonna using exactly the same function form. I'm gonna use exp, okay, minus half. Now I'm gonna put a square here, and I'm gonna put this thing in here, okay? So, however, the only thing that's different when I specify for function is that the similarities between these two functions is actually measured in terms of their parameter, mu1 and mu2. So all I'm really trying to do is I would put mu1 in here, and I'll put mu2 in here, okay? Is that okay? There you go. That's my undergraduate study, that's the introduction of RKHS for undergraduate students. Hopefully you understand that. Now, if for this to happen, there must be some conditions, yeah? What are the conditions? This function, right? This function, it must have a property in such that the parameter, this is the parameter, right? This is the parameter, okay? And this is the variable. So the parameter and the variable must what? Be of the same dimensionality. Otherwise, you can't just swap, right? In here is the, in here, this is the variable. And in here, this is the parameter. You can't just simply replace the parameter by a variable if they are not of the same dimensionality. So X, if it's RD, that implies like mu is also RD, yeah? So they are of the same dimensionality. And also they must be what? Symmetrical as well. So you can actually swap the role of X and mu. So you can swap them and the function value will be exactly the same. Yes? So last week, remember, I'm using this special notation. I'm gonna call it K, right? So I will call it K and I will put, mu1 in here. And this is a function, right? This is a function parameterized by mu1, yeah? This is a function, is an element of my RKHS and parameterized by mu1, yes? And this is a function that is also a member of RKHS that's parameterized by mu2, yes? Okay, and what's this? What's this thing? What's this? Talking about the notes last week. This will be the inner product of my RKHS using K as the kernel of this guy here, right? This guy here, K mu1, a function parameterized by mu1, and another function parameterized by mu2. Yep, and that should equal to K mu1, mu2. Yes. So that's what the kernel function will return. Correct? And that's it. That's your RKHS. Is that much better in understanding it using the Gaussian function? Well, I don't want to call it distribution because I want to get rid of that. It doesn't really have to be a distribution. So it's more generically, it's just a function, right? That function is a linear combination of a set of basis functions, which is the element of your RKHS. Okay, is that okay? All right. So is there any questions about RKHS from last week? If there is no more, by the way, has anyone have a look at the project specification? I will also type this thing in the lecture notes too. I just thought to hold on to that as well. So just to sort of explain it using hands. Okay. Well, the reality is I actually forgot that the first hour is the consultation. Otherwise, I was going to spend that consultation hour typing this. But anyway, so cool. And if there's well, I was very hesitating of releasing the project to you because everyone will be looking at the project rather than looking at the slides. So please do not look at the project specification yet. You have till the end of the semester to complete that. I actually set the deadline really, really far away from today. It will be the last teaching week, whichever Monday, the last teaching week, whichever that week might be. I think it's sometimes in December. Yeah, so the last teaching week usually is. Okay, so, and the whole project is about probabilistic graph models, probabilistic graphic models. So that's why I want everyone to pay a very close attention to what I'm going to be talking about today and also the subsequent weeks, because this subject, especially when you talk about variational inference, Monte Carlo Markov chain, these, and also a lot of the filtering methods these are all be using probabilistic graphical models. So yeah, today is just an introduction. So before I sort of talk about this, does anyone know what probabilistic graph models are or have heard of it? Okay. Yeah, if you haven't, this is a good time to actually learn about this. Okay, so firstly, I'm sure that you have heard of things like the Bayesian belief networks. It has got many names like belief networks, the Bayesian networks, probabilistic networks. I kind of just try to call them generative models. I will use the probabilistic graphic models to essentially depict them, right? To actually, because when I have a generative model, I can always use a probabilistic graph model to actually draw them out. I can actually draw them diagrammatically so that people can actually understand them. This is where well, I've about 10 years ago, my research is generally around probabilistic graph models. So the way we typically read a paper is to skip a lot of the words, just go straight to the probabilistic graph model, because once you read a model, you will actually know what the model is about, because it's a very clear way. It's very, it portrays the model clearly and unambiguously. And once you sort of look at the probabilistic graph model, you will be able to tell what its corresponding generative model is. And then from that point onwards, you will try to find where are all the innovations in that particular academic paper. So probabilistic graph model, it's not a mystery. It basically just tells you the conditional density. So it tells you that if you look at a particular random variable and you make them conditional on everything else, it tells you the conditional independence. So generally speaking, a probabilistic graphic model, it shows you the probability of a random node conditioning on just its parent nodes, okay? Just based on its parent nodes, like that. Cool. All right, so obviously this is not entirely true. This is not entirely true, because there's also an idea of something called a co-parent, which we will talk about that a little bit later, okay? And the edges are representing the causal knowledge. As you know, that the causality now, or explainable AI, becomes a very hot topics in machine learning. So that's why people love to use things like causal knowledge and things like that. All right, so okay, so enough said. I wanted to show you an example of maybe the first probabilistic graph model you have seen. I also used that example in my previous subjects, data mining, which actually has 0 prerequisite. That's why I can't talk about things too detail. But that's the example I'm using. So like that. And all of these stuff are your random variables. Okay, all of this. So A, B, C, D, E, they are all random variables. So, I mean, everyone here have studied some form of a Bayesian in your subject, yeah? So can I just ask, without looking at this probabilistic graph model, if I would say you have 5 random variables, A, B, C, D, E, how can you write the joint density? Like P of A, B, C, D, E, and using the Bayes theorem, how do you write it out in terms of its conditional and the marginal density? That's equal to P of A, condition on B, C, D, and E, right? And P of A, so B, C, D, and E, and times P of C, D, and E, times P of D and E, and times P of E. Yeah, so that's how you write it out. Is that the only way you can write out your conditional density? No. How many ways can you actually write it out? How many ways can you express this using just base formulation? It's 5 factorial, right? So the first node is any one of the 5. And next one is any one of the 4, and next one is any 3, and 2, and so on. Okay. So this is without actually knowing what? This is without knowing the conditional independence. Okay. Without knowing the conditional independence. What do I mean by conditional independence? Is like when I have something like this: P of A conditioning on B and C is equal to P of A conditioning on B. Because knowing C, it tells you everything. Knowing B, it tells you everything about A. It doesn't need C anymore, right? And you have seen it before. Where have you seen it? You say P of, remember when we talk about the Bayesian predictive filtering, we say P of Y conditioning on training, and this is equal to P of Y conditioning on theta times P of theta conditioning on Y, right? P theta. And we made a conditional independence assumption is that this will be equal to P of Y conditioning on theta and training Y, right? If you actually expanded out this, if you expanded out it according to the Bayes theorem, you're not going to get that. You're actually going to have this. But because we are assuming conditional independence, knowing the model, you don't need the training data, right? For your unseen data. So therefore, by the way, here is well, people made an underlying assumption. Your unseen data and your training data are of the same distribution. So therefore, once you have obtained a model, you don't need the past training data. Okay. Okay, so this is how you expand it out, right? How you expand this thing out. But the probabilistic graphical model, once you actually knew the probabilistic graphical model, you do not need to expand it in this way, right? Because you know all the conditional independence. And in fact, knowing the conditional independence, your conditional probabilities are actually become a lot simpler. Yes. Can anyone sort of guess what would be the corresponding joint density of this once you actually knew what the probabilistic graphical model is? Well, there you go. So this is corresponding to that, right? So you will take this branch here. You say P probability of B conditioning on A and E. Oh, I made a mistake, sorry. So it should be E. Probability B conditioning on A. And then times it by probability C conditioning on B. Because knowing B is enough. You don't need to know A and E. And then you will have this branch. So this one corresponding to this branch here. And this one corresponding to these edges here. And this one corresponding to these two, okay? Is that clear? I'm sure everyone knows how to do that in your project. Yes. By the way, your project is all about that. Easy? All right. So like I said, you know, if you expand it out without actually knowing there's a, you know, without actually know your probabilistic graph model, this is what you have to do. Like this is what you have to do, okay? I think today's lecture might be a little bit shorter than I had the slides for. So once we finishing that, I will spend some time to talk about the project that you need to undertake. And if we have some spare times, I'll probably go back to the RKHS because there are certain properties which I haven't actually explained to you. But most of the properties are actually quite straightforward. You can read by yourself on the note from the notes. But the important thing is the concept rather than the actual equations. All right, so, okay, all right. So now I'm going to show you somewhat a real example, which is not really that real, but just imagine, you know, now let's give a name to each one of this random variable, like say age, occupation, salary, and then determine if a person is going to be interested in buying. Like that will be the final one we try to predict. Okay. So if we actually write them out, it will be looking like something like this. Okay. So these are the three factors. Okay. And each one of them is a random variable. And then you have probability of buy. You have probability of buy, which will be conditioning on the age, occupation, and salary. Probability of interest in buying is only, you know, from, you know, like a buy intention. So that's the action, and that's the intention. And each one of these will have its own marginal probabilities. Is that clear? Like, this is time for people to ask a question if it's not clear. Yes. Oh, sorry. You are right. I also have to times these the other two marginal. Thank you. Yeah, I forgot. Okay, any other questions? Okay, no questions. I'm just gonna skip that. I think that's kind of straightforward. I think we will probably spend more time to talk about how they are used in the machine learning setting. So here's a concept called Markov blanket. Markov blanket. Markov blanket means that you know, these are the conditional independence random variables. So given the Markov blanket, that's enough to be conditioning on that particular random variable. You don't need anything else. So if we talk about this particular random variable, right? I mean, this is usually the data, but let's just say this is a random variable, and this will be its Markov blanket, because once you know this, you don't need to know the other ones. That is enough to make an inference for this particular random variable. Okay, so that's its Markov blanket. It just means that anything else apart from the Markov blanket becomes conditionally independent. So just that, yeah. So the probability of X conditioning on the rest of random variables equal to the probability of random variable conditioning on only its marginal, only its Markov blanket. Is that okay? Questions? Okay, so let's talk about the graphic model in machine learning. I don't know why we are going much faster than last week. I mean, the RKHS and also the PEC Bayesian. So not PEC Bayesian, the PEC learnable. Actually, these were slightly more conceptual, so that's why it takes a bit of time. And graphic model is actually one of the most practical research in probabilistic machine learning or statistical machine learning. So again, there are many different people using different notation to actually draw your graphic models. I like to stick with my own way of writing it. So unfortunately, you probably have to stick with the way that I design it, right? Which is still common, by the way. It's not something, but there's no standards how you can actually write a graphic model properly. So the way I write it is when you see a hyperparameter, like when you see a hyperparameter, you don't actually draw a circle around it. There's no circle around, okay? And when you have a random variable, you actually draw a hollow circle. You just draw a circle around it. And when it's a data or observation, you not only you put it into a circle, but you also having a light gray color. In LaTeX, I used to have an exclamation mark of 40. That's my preferred choice of color for the data. Why? And so let me show it to you. So here you go. That's a simple example. So can I ask what's alpha? What is alpha? Alpha is hyperparameter, right? And so what's theta? Theta is a random variable. And what's y? It's the observation or data. Is that okay? All right. Okay, so by the way, you know, this is a graphical model, right? That's a graphic model. It may look to you as if it's like why when we bother to draw a diagram like that, and when you only have a simple you know graphic model looks like this, it probably doesn't make too much sense. Like if you have a very simple model that looks like that, you don't really actually need to draw it. But if you have something very complicated, if you have some probabilistic model, which is, if you have a very complicated generative model, that's what we tend to use, right? We only have a very limited number of data. And in fact, our data isn't that complicated at all. But we try to assume the underlying model is actually very complex. And that's what researchers tend to do. Therefore, to actually draw the graphic models will have its advantage. Yeah, okay. All right. So let me give you a simple example of the things in this form, right? Let me give you a simple example of the things in this form. So let's have something like this. And can I just ask, what are these? These are the hyperparameters, right? What are these? That's the random variable, and that's the data. Yeah. Okay. So now remember all these arrows, they represent conditional density. Okay, they're all conditional density. Now, so I wanted to actually know what's so I'm just drawing analogy to this, right? So theta here now becomes my mu, right? So I wanted to say the mu, the probability of mu, is actually depending on these two hyperparameter. Yeah, hyperparameter means they are not random variable; they are constant. They're just you know for your prior, or for any of the conditional density, you have some parameter, right? You have some parameter. These are constant parameters, and so you define a probability this way. Yeah, I mean, we just say it's a Gaussian, and then you will. So this actually represent this part of the graph. Yeah, and this green stuff is represented by this conditional density. Yeah. Is that okay? Sorry, it's type graphic model. Okay. Now, so this is the mistake a lot of people are making. Even though people are working on generative model, graphic model for a very long time, I still see people making that kind of mistake. This is your assumption. So by the way, in your project, you need to make a lot of these assumptions. And by the way, you need to state why these assumptions are actually you know, are valid. So that's what statistical people do. They make assumptions. It's be like say you find a neural network. There's no assumptions. We just let the machine to figure out what are the values. So, but yeah, if you're doing statistical machine learning, you do need to make a lot of assumptions, like whether it's a Gaussian distribution. Especially, you are actually dealing with a lot of the latent variables. So when you're actually making an assumption, conditional density based on another latent variable, because the random variable and the variable it positions on, they're both latent. So you can't see them both. And that's why making a valid assumption needs to be justifiable. Okay, we actually need to make the story right. For those who are actually PhD students, and I'm sure that this is something that you do every day. Try to make the things that is justifiable. Okay, so here is the mistake a lot of people are making. What do you think these arrows mean? A lot of people think these arrows means dependency. Do you think that's true or not? So if you see an arrow like that, you say P of Y, conditioning on mu. So if you see an arrow looks like that, people will say P of Y, conditioning on mu, is not the same as P of Y. Yeah, they are not, Y and mu are not independent. But a lot of people will think that P of mu conditioning on Y is this. Is that correct? Mu and Y, they are independent. Is this correct now? So if Y is depending on mu, the mu will be independent of Y. It can't. They both are conditioning on each other. Okay? So just be very careful. The arrow doesn't actually, the direction of the arrow doesn't indicate dependency. So what does the direction arrow actually represent? If it doesn't dictate dependency, what does it represent? Causality? Or yeah, or more technically, what does it represent? I think tensor probability, what does it represent? I mean, causality is the right word, but it's more like more of a problem. But let's talk about just using probability. What does this directional arrow represent? It basically represents the conditional density you have specified, right? You have specified the conditional density. So you have specified this. So this is why I write down. It's actually represents the natural way of specifying the conditional density. So you basically specify your conditional density that way. So once you have specified your conditional density, P of Y equal to this, what about the reverse? So what's this? Do you need to specify it again? You don't. How do you actually get the reverse? So you have specified it, right? You have specified P of Y condition on mu. Then how do you get P of mu condition on Y? Bayes theorem, yeah, just Bayes theorem. So that's why you only need to specify one direction. The other direction is automatically computed. Okay, you can't specify two directions. It doesn't work. You might not match. Yes. Okay. So basically, if you wanted to do that, this is your posterior, right? So, I mean, if you look at that using the Bayesian terminology, this is the prior. P of mu is the prior. Okay. I mean, it may be conditional on everything else, but as far as Y is concerned, P of mu is your prior. And then you specify the conditional, and then you have your posterior, right? So if you look at that, that's your prior. That's your what? This is your what? What's that? What's this? What's this called? No. What's a not a tricky question? What's the name of this? No. If this is the prior, if this is the prior probability, what's this? Thank you. Likelihood. And what's this? That's your normalization constant, right? Normalization constant. So also is just P of Y. Yeah. Because you are essentially integrate out your random variable mu in there. Okay. So it's just like the base theorem you have. Like, so I'm just writing out like P of mu, that's P of Y condition on mu, and the other P of mu, right? So that's P of mu condition on Y. Let's go to that. Yeah, nothing special. Right. And just up to here, can I just make another? Is there anything else you have observed if you look at this equation here? If you look at this equation, right? If you look at this equation down here, and you look at this graphical model above here, what do you see? If you look at this equation here and look at the graphical model, what do you see? If you look at here and look at that, what do you see? Or maybe you look at here. So just let me remove that. Okay, if you look at here and you look at here, maybe more specifically, I'm just going to be looking at just that. If you look at this equation here, sorry, just give me 1 second. If you look at just this equation here, right? And if you look just this part here, and if you look at this equation here, what do you see? You see that every component, I mean, in fact, I think, let me take my word back. You have to look at the whole thing. If you just, yeah, maybe it's unnecessary for me to draw this diagram. So just look at this, but this and this and this. What do you see? You see that every component in here are defined according to your graphical model. Okay, so these are part of generative model, right? And so you can actually compute this posterior. Okay, I don't know, it's not exactly the right analogy. It's not exactly the right analogy. But if you think about how a neural network is trained, again, I just wanted to make a disclaimer, it's not a right analogy at all. Do you actually sort of see that your generative model or your graphic model specify your feed forward? It's probably not the right analogy, but you know, but in some way, right? When you actually train your neural networks, the feed forward, right? And the back propagation, referring to your posterior, okay, which are the things that you are interested in, which is much harder. Okay, you see the same analogy here, right? The feed forward is a lot easier, right? You just propagate whichever the data that comes in, and with the updated parameters, you are able to get the loss function. And then the back propagation is much harder because you need to compute your derivatives, right? But in a very similar fashion, you can see that your feed forward is specified by your neural network, right? Sorry, probably it's a graphic. And then these feed forward or these probabilistic graphical model components or these conditional densities will be used to computing your posterior. Okay, and that's what you are interested in. So remember, in your project, you need to compute this. Okay, you need to work out the posterior probability of all the model parameters, and the latent variables. And by the way, you're not gonna, if you submit something like this, you get like 5% of your mark. Because you're not gonna be working on a Gaussian distribution where you put the mean value as a random variable. That would be too simple for a project. The project needs to be very thoughtful, and you need to, again, we will spend a bit of time talking about your project, but you need to find your data and find your own model assumptions. The model needs to be, well, much more complicated than that. You have 3 people, okay? So I'm sure that you will be able to work things out. And then again, if you can't find 3 people, don't worry. You can do a project with 1 person too, if you like. And I am going to adjust my expectations of the outcomes and on how many people are in a group. So don't worry too much. You can find your partner. So yeah, so it doesn't mean that if you have a group of 1 person and a group of 3 people, I expect the outcome to be exactly the same. All right, so any questions before we take a break? And again, when we come back, I will show you 2 models, 2 sort of real graphical models. And you please expect the things that you submit for your project will be much harder than the models I'm going to show you. All right, so let's take a little break. And please come back at 4:30. Okay. Yes, yes. So this is the problem, and the version of by the way, it won't be the version. This version is talk about. Okay, so welcome back. I'm glad everyone come back at very punctually. So that's good. It must be that this particular topic is most interesting to people. I'm not sure whether the content is interesting or it's actually relating to your project. That's why everyone's very enthusiastic about this particular topic. I think probabilistic graphic models and generative models are actually one of the most interesting part of machine learning. Again, I'm biased because that's where I've been spending quite some time of my research and time in it. So, any questions about this graphical model? I mean, it's actually quite simple, right? There's a lot of notational things, but it's actually not hard about that. Okay, so then we actually just talk about this directed graph. And by the way, when you specify a probabilistic graphic model and the graph is a DAG, okay, it's DAG. What does when you say a graph is DAG? What do I mean by that? What's a DAG? DAG. It's a directed acyclic graph. So what's acyclic mean? Yeah, you're not gonna form a cycle, right? Because if you form a cycle, that's pretty bad. A going to B, and B to C, and C to A. Now it's not gonna have that. So it's actually directed acyclic graph. So it looks something like that. Can I just ask? This is called generative model, right? This is called generative model. What's the why it's called generative model? Why is it called generative model? Because you can probabilistically generate your data. Okay? You can probabilistically generate your data this way. Okay? So you can actually generate your mu from your first conditional, and from your mu, or you can draw a sample of mu. Okay? Does anyone know how to draw a sample from a distribution? Sample? Yes. I mean, using Python, presumably. But if you draw a sample somehow, right, from a distribution, and then you will put your mu into your new conditional density, you can draw a y out. Okay, so you can actually sample from your generative model. You can sample your data. People say, wait a minute, isn't the data given to us? Right? The data is given to you, right? So therefore, if you think about it, what does generative model tell you? Is to say, what are the probabilities of all your parameters and latent variables that have generated the y? Yeah. So basically, that's your posterior of your parameters and the latent variable conditioning on your observation y. Make sense? Okay. Right. Okay, so yeah, and when you have seen a directed graph, there must be an undirected graph. Yeah. So they are not really. So this, well, they're no longer generative models, but you have an undirect graph or something like this. In fact, if you have a mixture of direct and indirect graph, it is still considered to be a generative model for something. If you see something like this, and by the way, this is there's a name for it. It's called Markov random field. It's typically when all your axes, they are sort of like, in say 1 or 0, or so 1, 2, 3 to k. These are integer values. They are actually used quite frequently for segmentation purposes. Okay, and very typically used for image segmentation. So can anyone sort of tell me, from looking at this particular graphical model, which one are the operations? The x or y? Y, right? And the x, in terms of segmentation, what do they represent? If you are performing an image segmentation and your x's and belong to 1, 2, 3, 4, all the way to k, what do you think they represent? Think about an image segmentation. So if you are performing image segmentation, if you have like an image, right? If you like have a house here, and if you have a cloud here, and the rest of it is grass, or this is like the sky, and that's just the grass, right? So you probably see there are four segments. So each one of these pixels, so let's just say this is a pixel. This is like an xi, okay? It's an xi. And corresponding to that xi, you would have zi, yeah? Sorry. I'm just using the same notation as I had before. So yi is my pixels. Xi is the segment number. So if I have something like this, I would say 1, 1, 1, 1, 1. This is the house, and 2, 2, 2, 2, 2, 2. That's a cloud, and I'm gonna have something like this. Okay, I'm gonna 3, 3, 3, 3, 3. That's the sky. Okay, and I'm gonna have like 4, 4, 4, 4, 4, 4, 4, 4, 4 here. That's the grass. Make sense? So every pixel, you are actually creating another image, but this image only has 4 different. Every pixel can only have 4 different possible values, 1 to 4. Okay, and every value indicates which segment should that pixel belong to. Yes. Okay. So can I just ask a question? What's the why should you have an arrow and an undirected line between 2 segment number? Why that? So why you have this number here? Why this line here? If you want to perform image segmentation, what's special about image segmentation compared with, say, our cluster students? What's special about the image pixel segmentation? Yes, the pixels are connected. So therefore, the segment, there's more tendency for the neighboring pixels to belong to the same segment. Yeah. So if you look at these probabilistic graph models, you will see there's a little bit of probability right here. Well, there's not, I mean, that's the wrong word. There's not like a little bit of, there's a probability density here, right? Actually shows you how likely, so for example, if this value is say 2, right? 2, because the cloud is white, then the probability of this pixel being white will be very high. Yeah, I mean, I'm not sure if you knew about pixels like 2 to 5, 2 to 5, 2 to 5. So when you have RGB all equal to 2 to 5, that's very likely to be white. So this color will be having very high. So I'm just going to write like probability of 2 to 2, 2 to 5, 2 to 5, 2 to 5. Conditioning our, clouds, the cloud segment will be high. Is high. Maybe I will write like this. Say Y color. Conditioning on the pixel is actually, so I'll say ZI, sorry, ZI, just keep on. Maybe I'll say XI equal to clouds, YI equal to Y color is high. You get the idea? Yeah, okay. But I also have this kind of energy here, right? I kind of have energy to make a neighbor segment have the same number. Yes. Because it's no good when you're performing image segmentation. For anyone who actually works on the image, you will know that there's noises everywhere. So, even though in this house, you probably have a white color, a single dot. Someone maybe, I don't know, like, painted a white color in one of the windows. Okay? There's like a single dot. So you don't want that single dot to form a cluster, because that's kind of it. You have too many clusters. So when you are actually looking at this particular pixel here, you have two choices. Whether you have this kind of energy to say it should belong to the same cluster as its neighbor, right? So this energy tells you the neighborhood, right? Tells you the neighborhood pixels should belong to the same segment. And this probability shows you the probability it should be assigned to that particular feature, the data, right? So this is like the data-driven. So this direction is kind of like the data-driven, and this direction is like the neighbor-driven. Okay, maybe I'll put a spatial-driven or something like that. So this one is a neighborhood-driven. The other one is called feature-driven. Right? So it's like the energy between the two. So the analogy I typically tell people is that should this pixel belong to the neighbor with a different color? Right. Should belong to the neighbor with different color, or sorry, it's rephrase. Should that pixel belong to? Should have the same segment as the neighbor, which is of this, which should this pixel belong to its neighbor, or should it belong to its its feature? So which one actually has got higher energy? We'll put it that way. Okay, all right. So you can see that this direction between neighbors, they should what? They should have, well, there's no arrows to it. So when there are no arrows to it, it means there's not a single direction you can specify your conditional density. Yeah. And another word for it is to say that the probabilities of the two directions, they are symmetrical. Okay. Which means that if you swap one with the other, the conditional density looks exactly the same. So here you go. You have something like this. So this is the energy between the two. Right? That's what we typically specify for Markov random field. We specify a symmetric energy rather than a conditional density. Conditional density has a direction. T of A conditioning on B is generally not the same as T of B conditioning on A, right? But the energy is symmetrical. Here you go. Can anyone sort of tell me what does that mean? It just means that if the neighbor are exactly the same value, so for example, if both are cloud, so both are 2 equal to 2, so this one will be 1, right? And that will have beta, right? Beta. So you have exponential to the power of beta. And this is many of the pixels multiplied together. But if you just look at one thing, P of xi is proportional to exp, beta ij. So I should say, look, maybe I should So I need a pair, right? I need a pair. So I need to have P of xi, xj proportional to exp, then beta ij, an indicating function to say whether xi is equal to xj. Okay, so that's just for one pair, like one edge, right? So if they're the same, you get exp to the power beta ij, right? If they're the same, I'll say same. If xi equal to xj, if not, what do you get? You get 1, okay? If xi not equal to xj, okay? And let's assuming that beta ij is greater than 1. Which one is bigger? If beta ij is greater than 1, is this bigger or this bigger? Obviously, this is bigger, right? So therefore, you want to assign more energy when the two nodes will have the same segment. Make sense? So yeah, that's a Markov random field, which is I think using image segmentation for many decades. Any questions about that? But the important thing is to realize that when you have undirected graph, you are usually specifying into some kind of joint energy between the two. And the conditional density are symmetrical. Okay? Well, if they're symmetrical, you only can specify a symmetrical energy between the two random variables. Is that okay? Any questions? Okay, so no more questions. I'm gonna switch it back to the things that I'm gonna be talking about. Or the usual setting, or the setting that I'm gonna be concentrating in. And also in your projects, I'd imagine that most of you will be working on probabilistic graphical models, which have directed edges. Okay, that's what I'm anticipating. But of course, I mean, please try to use undirected edges as well. That'd be more fun. Okay. Obviously, you know there's no set of these projects will be very open-ended. So please feel free to make it as complicated as possible, but under the right assumption. So do not try to make your model overly complex just because you want to put 10 different variables in there. Okay? Try to make it anything that you put in, you need to justify. So here's another example of your probabilistic graph models. By the way, we will talk about this in detail in later part of this project, the subject, when we talk about filtering. Okay, so this is an example of filtering. This is the probabilistic graphical model for time series. Specifically, the filtering approach to time series. So this is different to auto-regression. When you see auto-regression, there usually is no latent variables. There is no X. There's only Y. You work on the observation directly. Okay? But for these filtering problems, we're assuming that every time you will have a latent state. Okay? So let me give you an example of tracking or filtering. Well, firstly, can I ask people, can you give me an example of a time series where you also have a latent representation as well? Stock price. Yeah, so stock price, these are the observations, right? These are the observations, right? That's the actual stock price. Okay, that's like, so if you look at certain, what's the word for it? segment, cross segment. Anyway, yeah. So if you actually look at certain stock price, yeah, if you look at any of the closing price for your stocks, okay. So this is something that you can observe directly. So that's like yesterday's price, that's today's price, that's tomorrow's price. And what are the latent representation in stock price? I mean, there's a whole heap of assumptions you can make, but just make one. When we talk about the stock, we will, how do people feel if I invite another senior quant to talk to you from competition at the math students for the next math cafe? Maybe I'll do that after the event. So yeah, I mean, just I'm obviously always constantly looking for the industry, opportunities for students, especially for the math students. So let me know what kind of people you would like me to invite and to give a talk. So at the moment, I think the senior quantitative analyst will be the most obvious choice, but please do let me know who you like to hear from. So yeah, do let me know about it. Okay. Right. So can you sort of nominate a latent representation of stock weakness? Something that you cannot observe. You cannot observe. By the way, this is something that you will be doing in your assignment. You need to think about a lot of the latent representations. Probabilistic machine learning is all about coming up with latent assumptions. So what are the latent things you can observe, which also is time variant, and that also varies with the stock returns. Any idea? I mean, there's no right or wrong answer. It's just a model assumption. It's no. The season. The season is something that you can observe. Too. Like what kind of season? Probably. The ethics. The problem seasons. But yeah, but let's kind of relate that to stock. Maybe like one of the latent variables is sentiment, right? Sentiment, the market sentiment. Okay, the market sentiment. So when you have the market sentiment, it's like people like is everyone selling or buying or holding or something like that, right? So this is something that you cannot observe because you can't observe people's sentiment. Right? You cannot observe. You're assuming there is a market sentiment there, but you cannot observe directly. By the way, this is something I made in the last 5 seconds. It might not relate to the actual how you predict the stock price, but in my opinion, nobody can predict the stock price anyway. So otherwise, yeah. So but anyway, so yeah. This is the market sentiment. So each one of these is like the market sentiment at this time, the market sentiment this time, and the market sentiment at that time. Okay, so you have some kind of latent representation of the market sentiment. But the Y is something that you observe. You actually observed your You actually observe your stock price. Okay. All right. So can I just ask, by looking at this probabilistic graphing model, would you be able to work out the Markov blanket? So if I wanted to say the probability of this node, okay, the probability of this node, when it's conditioning on all the rest of the nodes like this, okay, when it's conditioning on the rest of the nodes like this, what's its Markov blanket? So when we have say P of Y, okay, condition on the rest of the nodes, what is Markov blanket? What is that variable gonna give you the conditional independence, or set of variables that's gonna give you the conditional independence? Xt, yeah, xt plus 1. So it only needs, by the way, this is important. That's the most important part of the subject, okay? I mean, not the important subject. It's the most important part of probabilistic graph model to actually work out what is the Markov blanket. So P of yt plus 1 is conditionally independent of the rest of variables given xt plus 1. Yeah. So more generically, I'm going to get that. Yeah. I am going to get this. Okay. So I need to specify this. If I want to specify this model, I need to specify which corresponding to which arrow. So if I look at this, which arrow does it represent? If I look at this, which arrow does it represent? It's this arrow here, right? These arrows. P of yt condition on xt. Okay, so these are the arrows I represent. Yes. Okay. By the way, it has a special name. Does anyone know the name of this arrow? Has anyone ever worked on a filtering problem before? Probabilistic filtering. But it's actually called emission probability. Okay. Or sometimes people call it measurement probability. Now, if I look at another one, if I look at so if I look at this one, right? If I look at this one, and I want to work out the conditional independence when it's conditioning on these variables, then where is its Markov blanket? I'm excluding this one. Like I'm not counting this one. I'm just saying that this random variable conditioning on these, then where do you think it's the appropriate Markov blanket? Only xt, right? So which means that if I write them out more generically, I will have this, yeah? xt conditioning on xt minus 1, okay? But this is where I do not have yt in here, okay? Right, so I'm excluding this. Maybe I should make the notation, aligned. So instead of specifying that yt and I just make the last one yt and t minus 1 and t minus 2. Okay, but you see the idea. More generically, you can write like this. Cool. All right. So this is the time series. Just out of curiosity, what are we interested in computing? What are we interested in computing? So if you are giving a model like this, what do you think the most important? What do you think the most interesting part that you are interested in computing? We will talk about this later. We'll talk about filtering. I want to spend a couple of hours talking about filtering. There are multiple ways we can do filtering. But just for today, is anything that, what do you think the most important thing? What is the most interesting thing that you are, what is the most interesting probability that you are interested in computing, given this? Well, let me write it out for you. You are interested in computing this. Okay. So where is the Markov blanket for this? Anyone? By the way, what is this? Can anyone so tell me in word, what does this mean? P of xt conditioning on y1 all the way to yp. What does that mean? Tell me that in words. Yeah, given all your past data up to point t, right? What is the probability of my current state? Okay, yes. Given all my observations. So for example, using Chapman's stock example, I have, previous 1,000 days stock return, okay? And I want to know what today's market sentiment. Yes. I mean, this is my guess, but I think most likely it's used by some trading company. Okay, so is that it? Can anyone tell me what is the Markov blanket for? So which variable would you need in order to give you that conditional independence? xt minus 1. But there is no xt minus 1. Like my condition, the condition has no xt minus 1. So the correct answer is like there is nothing. There is nothing. We need all of them, right? Because I do not have xt minus 1 here. If I have xt minus 1, yes, I have my xt minus 1 will be my Markov bracket. But the problem is I don't have xt minus 1 here. I mean, the problem that you try to solve, people would ask you, like your boss will ask you, what's the market sentiment there? But all you have is all the stock returns. Your boss cannot tell you yesterday's market sentiment is this. Like, you know, that's something that else you need to figure out. So basically, this is the filter. Does anyone ever heard of common filter? No? No one has heard of common filter before. So common filter is used to track rockets. Anyone sort of told me and think about how is this thing relating to rockets? So what's why? So when people track the rockets, is this you have basically your ground stations, okay, and they take certain measurements out of your rocket, right? And your rocket will probably have some kind of sensors. Will also measure certain velocities and things like that of your rocket. Okay, so that's your Y. But what's your X? Is the true state of your rocket. Nobody knows, right? Nobody knows the true state of your rocket. So you need to do this. Okay, from a set of measurements, you want to infer the true state of your rocket. And can anyone sort of using the Bayes theorem to actually write it out this properly? So this will proportional to T of yt conditional xt, right? T of xt conditional xt minus 1. By the way, you don't need to write this down because I will derive this thing for you properly when we talk about common filter. So why do I know this? Because I've written this equation about 100 times already. It's one of the most classical examples in that. So if I actually write something like this down, right? What does it tell you? What does it tell you? By the way, you can derive this quite quickly. There's only 2 assumptions you need to make. All the rest of it is just a base formula. What does it tell you? So if you look at this equation here, you will see that, so remember we already specified this kind of conditional density, yeah? So this is this. You know exactly what that is, okay? Because you specified it. Like Chatham's question is, how do you make certain model assumptions? Yeah, you make them, right? You make your model assumptions. And you also specify that. That's your emission probability. That's your transition, by the way, it has a name called transition probability. So from the last state to the current state. Now, the only thing you do not know is the last bit. Is the last bit. Does anyone know, can tell me how do you deal with the last bit? Yeah, thank you. Does anyone else see that? You will have a recursion here, right? You will have a recursion here. So you don't have to deal with this. You do not have to deal with it because it's a recursion. So you just keep on recurring it back, right? So by the way, this is called the Bayesian recursive filter. RBF, Bayesian recursive filter. Common filter, particle filter, they are all part of your Bayesian recursive filter. So just out of curiosity, if this is a Gaussian, if this is a Gaussian, and this is a Gaussian, what do we have? If you have an integral, so this will be dxt minus 1. What do you have? That's also Gaussian, okay? And if this is Gaussian, obviously this is Gaussian. Well, we designed it to be Gaussian, and that's also Gaussian, right? So, and so which means that if you design all your emission probability and your transition probability to be Gaussian, everything stays Gaussian. And by the way, that's common filter. That's what Dr. Carmen has designed in 1960s. And that kind of revolutionized the whole tracking business. Okay? Because computation is super efficient. If you have everything in Gaussian, all you need to do is to update the mean and the covariance matrix. That's all you need. So yeah, so that's it. 60 years ago, and people are still using it. Right. And I'm sure that some trading companies are still using common filter to do their tracking. Okay, so enough said about this. Now, are you ready to see a real graphic model? I mean, this is not, it's still an educational graphic model, still not real. Okay, it's somewhat getting real. One, I can have 20 examples of things that I've been working on. But you cannot, you have to think about something new. You can't just grabbing like a paper and redraw the graphic model. That's called cheating. You have to actually design your stuff yourself, okay? You have to have your own data set and the right assumptions and so here you go. Here's a Gaussian mixture model. So what's a Gaussian mixture model? We have talked about that in the data mining class, but who has seen a Gaussian mixture model before? So just imagine that I try to model that people come to BU, okay? I actually model the time of arrival for people to arriving in BU. What time do you come to university? Like in the morning, or do you just come to this class? What about PhD students? What time do you normally come? Like 12 o'clock. Okay, so I'm just gonna say maybe I'll say 11 o'clock. So this is like a lot of people will come, right? So if I actually try to work out the time of people's arrival, you will see there's 11 o'clock a lot of people here, and then 6 o'clock people will be coming for the night classes, something like this. Okay, if I start plotting everyone's arrival time to the BU's gates, it'll be something like this. And I said if I wanted to model this using a Gaussian distribution, is my model assumption valid? So if I have this kind of observation, maybe I'll make it even more exaggerated. I have lots of arrival here. Okay, lots of arrival here. So and I want to say that I can explain this data using a single Gaussian. It is valid. Or not? By the way, this is a very typical example of how you would, even if you become a data scientist, this is like the problem I'm sure that you will face in your first 6 months of your work. And can you actually plot a single Gaussian to explain this data? No, you can't. What if you're using a Gaussian for the data? By the way, if anyone remember the maximum likelihood estimation of your Gaussian mu, it's just the sample average. Yeah? So you're actually going to get something like this. You're actually going to get a Gaussian distribution like this. But what's the underlying assumption of your Gaussian distribution? Is that the data under your mu will be most dense. But you look at that, it has no data under mu. So it's actually the least dense block, right? So therefore, this should not be explained by a single mode Gaussian. And then if it's not explained by a single mode Gaussian, what kind of distribution should it be? Maybe 2 Gaussians, yeah? I'll have this Gaussian. I'll have another Gaussian like this. So how do I define a Gaussian mixture model? I would say P of X is equal to sum, okay? The sum of 2 Gaussians, L to 1 to K. Then I have X, this is something I'll try to model. And I'll have a mu L and sigma L. Does anyone see the problem in that if I do that? Yes, if I try to computing the integral of this, if I try to compute the integral of this, I get what? K, right? I get K. So obviously that's not possible because I'm dealing with a PDF here. So what's the appropriate way of doing that? Is I will have a weight where sum of weights equal to 1. Okay, so that's a Gaussian mixture model, right? And the usual Gaussian mixture model, which by the way, I'm going to talk about expectation maximization. How do you perform maximum likelihood estimation of these parameters? Believe me, computing the maximum likelihood estimation of Gaussian mixture model is a lot harder than a single mode Gaussian, which is something that you typically study in your first year stats course. This type of models, we're going to use something called expectation maximization, which will come later. I kind of changed the subject schedule a little bit because I want to talk about probabilistic graph models, so you can think about your project a little bit. Right? So if I have something like that, okay, now I'm going to make the problem even harder. I'm going to say each one of these is a random variable. Okay, all of these are actually random variables. But I'm going to simplify things a little bit. I want to make this stuff 1D, make X 1D. Okay, and I'm going to stick with only two Gaussians. So I'm going to stick with a problem of only 2 Gaussians. So I'm going to say this is a mu1, okay, mu1, right? And mu1, which will have, this is the precision. So this will be 1 over tau, right? So this is mu2 rather than mu2. I'm actually making mu2 a dependent variable. I'm going to say the two of them are theta apart. They have to be theta apart, right? And the theta itself is a random variable. And I'm going to make it also the precision 1 tau as well. So the variance is 1 over tau. Okay, the variance is 1 over tau. Okay, and so the weight, remember you might have lots of people coming in the morning, right? You might have lots of people coming. You maybe only have a tiny bit of people coming after hours. So this distribution supposed to be a lot higher, like this one, okay? So the weights in here are different. So this weight, maybe this is greater than that, okay? So they might not be the same. I'm just gonna say more generically, just saying that they don't have to be the same. So it can go either way. So you understand this, the problem that we're trying to have model. And all of these parameters, they are random variables. Okay? All these parameters, they are random variables. So you are enjoying probably the graphic model. This is just an educational purpose. Okay? The next model I'm going to talk about today will be real, but it's like 15 years ago. Okay, so we have something like that. Now the problem is this: we need to think about, a proper prior for each one of these random variables. Okay, so before we think about the prior or the appropriate densities for each of the random variables, what's the first thing you need to do? If you try to come up with a probability for this random variable, what is the first thing that comes to your mind? So if I wanted to model like a length of a chair, right? Would that be the same as modeling the number of people have arrived to the parcel? Is that going to be the same distribution? No. Okay, no. Why? Because the support of these random variables will be different. And please take my advice. The first thing you think about is the support of a random variable. So what's the support of this random variable? So we're going to talk about, say, support of X. I think some people just using support X is where for all X such that P of X is greater, not greater, equal to 0. Okay. So, and so let's think about it. What do you think this theta? What's the support of theta? Remember, it's the difference between well, it's not really different. It's actually just the offset. So it can be either left or right. Because we just need to adding. We can add mu2 from mu1 by adding a theta to it. I just realized that I actually forgot to tell you something about covariance, but let me get back to that. Yeah. Okay. I will talk about covariance a little bit later. But so, what kind of support is for theta? It's basically the real number line, right? Okay. So, what kind of distribution do you think? So, if the support for theta, so if support for theta is the real number line, and what is the plausible distribution for it? If a random variable has got probability greater than 0 across your whole number line, what is the first thing comes to your mind? Guessing. So here you go. That's why we have chosen it to be that, right? Can anyone sort of tell me what is this guy? What's this one? This is called. Huh? This is for the more generically. What's this? In terms of graphic model, this sigma theta is what? It's a fun graph. It's not a random variable. Okay, so you just need to be very careful. By the way, some people use that as a random variable. If you use that as a random variable, you need to define another distribution for it. Then finally, you can put another random variable. So you can keep on going. There's a, I think it's fine. Well, there's a very famous machine learning researcher. His name is Zhang from Beijing University. I had a chat with him 5 years ago regarding deep learning, and I think his view is to say, if we put, a data network where we have, hyperprior over hyperprior over hyperprior, maybe we can achieve the same thing of having a deep learning with layers of layers of neural networks. Again, that's just a thought. But anyway, so coming back to this. So we have something like that, right? That's the hyperparameter. Okay, so, and what about mu? What about mu1? Because mu1 can take any value in the real number line. So we will assign a Gaussian distribution as well. And this would be a hyperprior as well, right? So it would be the hyperprior for that as well, because it does not have a, it does not actually have a, well, it's not a random error. So this is which I wanted to use a way of writing it as just mu2 is equal to mu1 plus theta. Yeah, okay. That's fine. Okay, so here comes another interesting. By the way, everything I specify here are the most common distributions for probabilistic graphical models in machine learning. And these distributions actually all have a name. They all belong to something called the exponential family distribution. Have you ever heard of that before? You haven't? That's fine. We will talk about them later. Right. So yeah. So yeah. And well, we'll have to talk about them later, because there's also an idea of a natural parameter and also conjugacy. Has anyone heard about conjugacy? Something being conjugate. What do I mean? What's the meaning of conjugacy in probability? In probability, is the posterior and the prior are of the same type of distribution. Okay, this is called conjugacy. Okay, so anyway, we'll, no, we will not talk about that. Okay, so actually now time's up, really. So we need to take a 10 minutes break, and we will come back, and let's come back at 5:30, and we will continue with that. Unfortunately, there's no time to actually go back to the RKHS. I think we just have time to finish the other two. Well, after that, there's another example on 38. I think we'll, that'll be good. That'll be enough for today. Okay, so let's take a 10 minutes break, and I'll see you guys in 10 minutes. Oh, got it. Yeah, so did you see that? Yeah, sure. Did you see that the notes I just write? I think I just write something down like this. Do you see this equation? Yes. So these are your configuration points. These are the corresponding image locations, right? So did you see that for each one of this grid? So okay, so I need to do this. Oh, sorry. I don't know why I pressed that. It's, yeah. So what happens is that if you have like a grid that looks like this, yeah. So this is the frontal view, and if this is an image view, okay. So you know that these points and these points are corresponding. Yes. Yeah. So if these are corresponding, then this point should be x1, and this point should be uv1. Okay. So you know that when they are actually corresponding, you can actually get this equation. Okay. So once you understand that, there's a homography that maps this point to that point. Okay. So when you have something like this, you know that you actually generate these two equations. Yes. Yeah. So when you generate these two equations, your H is a vector which contains H11. So H11, H12, H13, H21, H22, H23, H31, that, okay? So you contain that vector. And I need you to think about it. How do you get this matrix A? So what you are really doing is that you are getting these two equations, 1 and 2. And this is your H11, H12, H13, and so on, okay? So you get two lines of that equation, yeah? Then the more points you are going to have, you are adding another two more lines, okay? Then another 2 point you are having, you're gonna have another two more lines, yeah? And then just keep on stacking to it until you get a matrix A, which has got more lines than the number of unknowns. And then you just solve that.
This two line is UN.
Yeah. Well, you need to think about it. How do you actually convert something like this into these two lines, where the H are your unknowns, and these two lines are corresponding to these two equations. Is that okay? Is that understood?
Not really.
Not really. Okay.
So the first row is U and the second row is Y.
Okay. So this point, you understand this point is your XY, right?
Yeah.
Okay.
Yes.
So you understand this is corresponding UV, yeah? So you mean, and this is something you do not know. You do not know this, okay? So therefore, from this equation, you will be able to get that. Yes, okay? And from these two equations, you will be able to get into a situation where you have an H here, and you will append two rows of the matrix A. Is that okay?
Oh, also, I need to rearrange this.
Yes,
This
yes. You need to put
together.
H in your unknown,
Oh,
and the matrix A, which and it'll have two rows. Is that okay?
okay, thank you.
Okay. Actually, for a minute, I just thought my laptop was dropped on the floor, so I was a bit worried. So I think I have a few students coming to ask me questions about the homework. So I wanted to tell you that unless you specifically told me not to, tell discussion with the rest of the class, I am anything I tell one student, I'm going to share it with the rest of the class. Hopefully that's okay. So if you do not have time to come to see me for consultation, and that's not going to be disadvantage to you. But if there are certain things that you do not want me to share with the rest of the class, please do let me know. Otherwise, I shouldn't share with you. So anything I explain to the student, I'm going to type out in the email, and I will send it to everyone. Regarding the homework or the project, project may be different because it's kind of you have a very long time to actually complete that, and it's in working in groups. But certainly that would be my policy of answering students' questions regarding the homework. Okay, so with that said, I'm not sure. Oh, all right, so with that said, I am going to go back to our very exciting topics of the school. So as you know that the project is actually worth 35% of your entire subject. Do you all realize that there's a change of marking things for all your math subjects? Yeah, so basically now the final exam is only a very tiny portion of your marks. But that's going to mean that you need to study very hard for your final exam as well. Okay. I'm not really sure whether there's any marking criteria to say must pass the final to pass the whole thing. I am not sure. I'm not sure. I need to check. But whether you actually see it as a good thing or a bad thing, but the homework and also the project now accounts for a very significant portion of your subject. Unlike in previous years, I'm good to you, so I'm also adjusting to this. But you know, when I was in Australia, that's usually the case. The final exam is usually was very little, and the task component in the project is actually a lot. Especially if in the computer science department, the project usually involves a significant programming. So I try to remove that from your subject. Do people know how to program? You don't know how to program, right? Maybe I should put some programming in. It's extra fun for you. All right, cool. So yeah, so let's coming back to this. So we have actually talked about, assign a proper, distribution, or the we need to find the proper appropriate distributions for all the marginals and conditionals in this particular, graphical model. So can I just ask, what about W? So W1 and W2, basically they need to have this, they need to have the same distribution. They need to be treated as a vector, okay? Because why do they need to be treated vector? Because they add up to become one. So what do you think is the most appropriate distribution for them? W1 and W2. So if you actually try to sample a distribution where the element of this vector needs to add up to one, what kind of distribution you got? It's weights? No, I mean, these are the weights. So W1 and W2 need to add up to one. So W1 plus W2 is equal to 1, and Wi is going to be greater, so they need to be within 0 and 1. Okay, so they it can be a number between 0 and 1, and needs to add up to 1. Thank you. But let's okay. Let me come back to this a little bit later. Let's actually. Oh, thank you. But let me make the problem a little bit more. So okay, let's talk about Chaplin's solution first. Chaplin, what's your solution? Very good, very good. So I mean, so Chaplin has realized that because we are only having two, we are only having dimensionality of two. So all we need to do is just to model the probability of W1, and W2 is equal to 1 minus W. Okay, that's a special case. Now, if that's the case, what kind of distribution would it be? Or do you think it's appropriate? Which distribution has a support over, has a support between 0 and 1? Beta distribution, right? So you can actually have a beta distribution. So W1 is beta, right? Whichever the hyperparameter is, and W2 is equal to 1 minus W1. All right, so the problem is that let's make it harder. What if you have 3 dimensions? There are 3 mixtures. Then what? You can't use beta anymore. In fact, you can still use beta. But there's a trick I want to tell you. But just imagine that you have 3, and W1 plus W2 plus W3 equals 1. What kind of distribution would it be? It's a delation distribution. So W1, so I would say W more generically is equal to delation distribution of the alpha 1 to alpha k. If this one has if W has dimensionality of k. So beta distribution is a special case of delation distribution when you only have 2 dimensions. Okay, when you only have 2 dimensions. So just by the way, if you look at W1 and W2, where can you plot the support? Where can you plot the support? So this is W1 and W2. Where do you think the support is? Where do you think is the space in which it has got non-zero probability? How do you plot it? It's this, right? So that's 1, 0. And this is 0, 1. Now, what if we have 3, like W1, W2, and W3? So how do you do that when this is 3? So you will have something like this. So this is 0, 0, 1. This is 0, 1, 0. This is 1, 0, 0. And you need to draw something like that. Does anyone know the name for this kind of stuff? I mean, you can also plot a 4D, 3D, right? But does anyone know the name, generic name for something like this? It's called the simplex. So this is a 3D simplex. This is a 2D simplex. And you can also plot the 4D simplex. You can't plot 4D in general, but you can plot the 4D simplex. Okay, so all right, so we have decided that we're just gonna using a 2-dimensional delation distribution, or 1D beta. The other one is 1 minus that. That's fine. And how do you draw Z? I mean, what's Z? Z is the latent variable. Actually, it tells you that. So I need to erase something, right? Let me just erase this because it's really maybe not. So if I actually pick a particular X, I'll say, hey, this is X. This particular, so this is Xi, which has a value, and I want to say the corresponding Zi. So do you see that all these X's, which mixture should they belong to? So if I give a name for it, this is mixture 1, this is mixture 2, and all these X's in this Gaussian, they should have a Zi, which component it belongs to. All the Zi values should be 1. 1. So I mean, this diagram is very cluttered. So I'm just getting a new one. So I'm gonna have a distribution look like this, okay? Distribution looks like that. And I have this value to be x1. I have this value to be x2. And because I call this distribution as 1, call this distribution as 2, so the corresponding Z1 will be what? 1. And the corresponding Z2 will be 2, okay? So if I have a data that's in here, I'm gonna call it x3. What do you think the corresponding Z3 is? 2, okay? So the Z is the indicator of which Gaussian has distributed that this data is belonging to. Okay. Can I ask what's the significance of that? I mean, this is a latent variable. You do not know. You do not know which Gaussian distributed that data. So what's the significance of that? The indicator random variable has been used in probabilistic machine learning throughout. So you have to get used to it. And I sort of anticipate you probably will use that in your data as well. Okay. In your project too. So you have to get very used to the idea of having a latent representation of the component index. So what's the significance of that? So if I actually now specify P of, remember, this is hard, right? This is hard. This stuff is hard because I'm dealing with a Gaussian mixture model, and that's kind of hard stuff. So this stuff is actually hard because, you know, I'm trying to adding a multiple Gaussian together. But once I actually knew which data have which Gaussian distributed, my data is distributed from which Gaussian, how does it simplify things? So if I have something like this, right? So if I have P of xi conditioning on zi, and also the rest of stuff, also the parameters like theta, and that becomes what? A Gaussian of xi if I knew exactly which Gaussian has distributed my data, and then what's that? Is that still Gaussian mixture model? No, it's what? So let me repeat again. So if I knew, like, you know, when the reason I have a Gaussian mixture model is that this possible data, this data can belong to either this or that, right? It's more likely to be distributed from this distribution than the other one, but it has a probability to be distributed from either one of this. So that's why you have some probabilities coming from this distribution, this below probably coming from here, and you have this amount of probabilities coming from this distribution. Yeah. But if I knew, if I was able to tell the system that this data is distributed from this Gaussian, okay? If I know its membership index, right? If I knew its membership index, then what does this probability simplify down to? Anyone? Zi and theta. Theta is like all the rest of parameters. That's equal to the Gaussian of xi and what? Mu zi, right? Which Gaussian it is, right? And then you have your power, okay? Decision matrix. Yep. This is important. Not only important for your project for this particular stuff. When we talk about EM, it's exactly the same assumption. In fact, half an hour later, when we talk about relation rate allocation, we will talk about exactly the same latent membership indicator. And believe me, if you ever work on probabilistic machine learning, this appears in nearly half of the things. Okay, so just sort of get used to it. Get used to this idea that you have a latent membership indicator. All right, that's all. I mean, we are pretty much done here, right? And lastly, we have the precision stuff. We have the precision. Precision is the inverse of your variance. So what kind of distribution do you think is appropriate? Okay, think about like a variance. Variance, what's the support for a variance? Is that like a real number line? What about like a variance, for example? You can't have negative variance. So it has to be non-zero, right? A positive number line. So what distribution do you think is appropriate for positive number line? There's actually quite a few. The thing that we use most often, I think what Chapman said last week. If it's 1D, it's a appropriate one to use as a gamma. Okay. So if you look at the shape of gamma, it looks something like this. It depends on the parameter of gamma though. It's like some, it looks like this. Or sometimes it looks like this. Depends on the parameter that you use. But the support is it's non-negative, right? The support is non-negative. I think the support is positive, sorry, it can't be negative. It can't be zero, so it can't be zero. So it's that the support is positive. Okay, so that's I mean, you also can use something like chi-square, but gamma is used a lot. And the reason of that is because it's actually conjugate. Now, that's not entirely true. So, okay, I'll say it anyway. So basically, if your mu and sigma square is distributed according to normal gamma distribution. Normal gamma, it doesn't mean a normal and a gamma multiplied together. It's actually a normal gamma distribution. Then the posterior is also normal gamma. So that's why they are actually, so let me actually write down the, so yeah, so maybe P of that. So normal gamma, and then I would multiply proportional to an X. So that is Gaussian, where the parameter is distributed to a normal gamma, and the posterior is also a normal gamma. And that's one of the reasons that we actually love to use the gamma distribution as opposed to chi-square, which also kind of does that. But then again, chi-square has got the probability of acting. Is all the lucky. Okay, so, and of course, the thing that we are really interested in is this, right? Now, this is a good time when I get rid of all my annotations. So things that I'm actually interested in, ooh, it takes so long to. So the things that I'm actually interested in modeling is this. The posterior inference, which is something that you need to do in your project as well. So we need to, because these are all random variables, we need to work out the posterior distribution of all your parameters. And so, I mean, there is no clear definition of what is a parameter and what is a latent variable. I mean, sometimes it's kind of quite blurred. But typically, like the membership indicator, these are actually the latent variables, okay? Latent variables. So they should also have a round circle to it because it's not a hyperparameter. But these are your parameters, okay? These are your parameters. But you know, you can sort of argue that the weights should also be a latent variable too. So there's no clear cut. Okay. So basically, you need to infer all these stuff. Everything you have a round circle, sorry, not round circle. Everything you have a circle around it, and you need to perform your posterior inference. Cool. Right. By the way, it's a good skill to have anyway. So you're not gonna. I think if you yeah. Sorry. Okay, now you're ready to. Sorry, and I think you also see something, which is this. What do you think this thing tries to do? Take a guess. I think it's sort of fairly self-intuitive. What do you think? Why do I draw a rectangle around it and have a letter N? Because I have N data points, yeah? So if I don't do that, I have like Zi goes to Yi, sorry, Z1 goes to Y1, Z2 goes to Y2, Z3 goes to Y3, and so on. I need to repeat this N times, which is totally unnecessary. Okay, that's why I have something like this. And this is called the plate. Okay, this is called plate. So I have a plate. So yeah, again, I just sort of illustrate that. These are identical. So these are identical. So when you have A goes to 3 variables, B1, B2, B3, it's the same as, you know, A goes to BI only, but that would be 3. It's just a simple way of writing. Okay. And you know, if you are doing, obviously everybody here does data science. When you do data science, you never ever have to do with only one data. So you will have multiple copies. So you have multiple data points. So that's why you probably use text. Okay. So is that clear? I think now this is a good time that I need to explain what's called parent. So parent is this. Like if you look at this kind of structure, you probably think that you're going to have, so what's P of A conditioning on C? So you probably think this is true, right? You probably think that P of A conditioning on C and B is equal to P of A conditioning on C. Yeah? Yeah. I mean, without knowing this co-parent relationship, this is probably what you are, right? So who agree with me? Yeah. So who agrees with me? Who thinks this is true? Yeah, okay, who thinks this is true? Anyone else? So who thinks it's false? One versus one. Who's winning? What about everyone else? The English expression called sitting on the fence. Everybody sits on the fence. So this is not true. Okay, this is not true. This is a very special case of the probabilistic graph model. It's called co-parents. So the example I typically try to use to tell people is that imagine A is the true color of a ball. Okay, this is like the true color of a ball, and this is the lighting condition, and this is the observed color. Okay, so when you try to infer the true color from just the observed color, because what if this lighting is actually really sort of green, and you observe this ball kind of to be very greenish? Yeah, the probability of being green is very high. But in fact, you cannot do that until you also know the lighting condition. Yeah, because both of these are adding to it. Both of these factors are adding to it. So you cannot decide the probability of one factor without knowing the other factor. Okay, you can't, knowing the sum of these two factors are not enough. So you know what I mean? Like this is the one factor you can't decompose. You can't decompose this unless you know how much the other factor is. Right, so this is called co-parent relationship. And please be be very, very mindful of that. Okay, so the last one I wanted to show you is a real example. So this is a paper written by David Bly, who's a very famous researcher in statistical machine learning. And the LDA has been kind of around for a very long time. The paper was published in 2003. I think it was published PhD thesis. And it was and the paper and this particular approach was the go-to approach to do unsupervised document clustering. Okay. So I use the exact same example as we have done in the data mining subject, but this time around I'm going to talk about generative models in detail, and you also need to perform the theory inference on that. So so that kind of gives you a very simple baseline for your project. The project needs to be much harder than that. Okay? Because that's like 20 years ago. So the idea is this: why we need to do document clustering is this. Well, there's multiple reasons why we need to cluster documents, right? But the idea is that if you have this document, right? If you have multiple documents, I basically just go to Wikipedia and actually download the paragraph for HKBU. So you need to figure out with every single document, what is the latent representation of that document should be. So if you have, like, say, a document 1, you have a document 2, all right? You need to convert that document into a feature representation. And that vector representation needs to be of the same dimensionality. What is that? What do you need to convert document 1 and document 3 to a vector representation of the same dimensionality? Why do you do that? Because you can then compare, right? So if you want to build an application that people say, look, how to find the most similar documents. Right? Imagine you are performing some kind of legal search, paralegals, and you put in your new document, and you can't actually performing the search by using the original representation. It just works, right? Document just works. And document 1 probably will have 100 words. Document 2 maybe have 50 words. You can't actually compare 2 documents because in the original form, it's very hard to compare. So you must convert a document, which is a set of paragraphs, into a latent representation. Okay. Right. So the idea is that what are these latent representation actually indicates the percentage or the weights of the topics. So T1 to TK. This document will have T1 to TK, but they will have different proportionality. Does that make sense? So every document talks about different topics. Yeah. Right. If you read a document, you'll say this document, 20% sports, 80% entertainment. The other one is 80% entertainment, 20% sport. Yeah. But you appreciate the fact that we cannot see this information directly. It's all latent information. Yeah. Okay. So you need to infer these topic distributions out of that. Okay. So each document will have a topic distribution. So that's why so does this name sounds okay now? Why it's called latent? Because the topic distribution cannot be observed directly. It's latent. What about delay delay? Because the topic weights are distributed according to a delay distribution. Allocation just means that every document has its own distribution. Okay. Yeah. All right. So, and that's it. Let's have a look at this graphic model. Now you have everything to understand this probabilistic graphic model. Okay. So can anyone sort of explain that to me? What's going on? Now, I'm saying that theta So I have D documents. I have big D number of documents, yeah? Okay. And I have got, this theta D is the topic distribution assigned to every single document, okay? Yep. So I have like this document, you know, just like what I have here. So this will be theta 1, this will be theta 2, right? So every single document has its own topic distributions. They're all gonna be different. Is that okay? So that's why you have that, right? And this is the hyperparameter for it. So can I just ask, what's theta D? If I write out its generative model, it should be what? The Dirichlet distribution, where alpha is the parameter. Okay. So they all, well, you can design it in whichever way you want to, but the model will use the same parameter for all of them. That's a pry for that. Now, what's beta K? Beta K is this. So the underlying assumption is not just that. Every single topic will have its own word distribution. Okay, so that's the first word. That's the last word, okay? So you understand that? Kind of, if it's entertainment, I actually have an example for you. So for example, if you have an entertainment, right? So, well, the first thing is, well, let me actually show you an example. Now, this is document number 1, okay? And this is number 2. So the very first thing is to say, let's convert them into tokens, right? And now if I actually look at word 1.5, so that will indicate it's the first document, the 5th word. So you can count them 1, 2, 3, 4, 5. So it's college. And the second word, which is W2H, means, you know, in the second document, you have 1, 2, 3, 4, 5, 6, 7, 8, which is Baptist, right? So, and these are the only observations you have. You have W1, 1 to W1N. You have W2, 1 to W1, because they have different number of words. So you should have something like, you know, like W11, okay, to W1N1, okay? And then you have W121 to W2N2, okay? And so this, well, I mean, this is kind of just for illustration purpose. Usually, the first thing you need to do are not treating every single word as a token. There's a pre-processing step as well, which I'm going to skip because that's really to do with natural language processing. People will tend to group certain words together, like Hong Kong will be treating it as a single token, okay? For example, you know, Yonglong will be treating it as a single token too, okay? And and there's a few pre-processing involved. But just for the purpose of this subject, let's just consider every single word as a token, right? Okay, so so that's kind of your observation you have. So now you can see that these are the observations we have. Remember, anything that's having a light gray color is your observation. Everything else you need to infer, okay? Maybe I shouldn't draw like a circle around to so confuse people. And this is just a hyperparameter. A hyperparameter, we don't need to do anything because we just dominate them, right? So now you get the idea that every document have its own topic distribution, and every topic have a word distribution, right? So if this is topic is sport, then you know the word Yang Loman will have very low probability, okay? And you know let me just you know, Siobhan Hohi will have very high probability if it's sport, okay? So, and if the second topic is actually a entertainment, then, you know, like a pop star will have very high probability, whereas a sports star will have a very low probability. Yes, but then again, these days, sports star and entertainment star are actually the same thing. Okay, so let's just, for illustration purpose, you get the idea, right? So let me just rephrase. The whole latent relation allocation has two assumptions. What are these two assumptions? Every single document has its own latent topic distribution. Every single topic will have its own latent word distribution. Okay, so you can imagine that the topic distribution associated with every document will be very short. The dimensionality won't be very high, but the word distribution associated with the topic, that's huge, because that's every single possible word in the word corpus. Corpus means collection of documents. Yes. Okay. So you understand the model assumption. Okay. So understanding the model assumption is the start. Let's have a look. So the theta d, which is the topic distribution, which will come from a Dirichlet distribution, yeah, where this is the hyperparameter. What about beta k? What about beta k? Beta k should be what? Beta k should be what kind of distribution? Beta k should be, I mean, what's beta k? Beta k, well, I haven't actually told you, so I don't expect it to. So beta k is the word distribution for every topic. Apologize for that. Because I've been looking at LDA for I've been working with LDA or the variant of LDA for a very long time. I kind of just, you know. All right, so beta k is essentially the distribution of words for topic k. So what kind of distribution should that be? I mean, when you talk about a distribution will have a probability. The first probability you will come to your mind will be a Dirichlet distribution. Yeah? So it's also a Dirichlet distribution where this eta is used as a parameter for that distribution. Is that okay? So here are the two model assumptions that we have. Right? Here are the model two assumptions we have. So every single document have its own topic distribution. So topic distribution. That's just word distribution for a topic. Okay. Right. So then what's ZDN? If WDN is the nth word of this document, then what's ZDN? So WDN is, remember the example I'm using here. So W15 is the fifth word of the first document. W28 is the eighth word of the second document. So WDN is the nth word of this document. Then what's the corresponding ZDN? Remember that X and Z that we talked about just before, or X and Y. Z will be the which topic that this word belongs to, right? Which topic that word belongs to. Yes. And by the way, this is the most confusing part. Once you get that, you'll find LDA like that. Okay, so before we talk about this, what do you think is the probability of ZDN? So probability of ZDN is which topic have generated WDN. Yeah, and say WDN is the nth word of this document. So the corresponding topic number for WDN is ZDN. So what's the distribution for ZDN? What's the probability of ZDN? Remember this. remember this. For document D1, we have theta1, which is the distribution of topics. So Z1 and I should say Z11 for all ZIs, they should distribute it from what? Doesn't need to use differential again. You can just using multinomial distribution, right? Multinomial distribution, and it's actually come from theta1. Because theta1 already tells you the weights of every topic. So if you actually draw, so for example, I'll say, just imagine, say, theta1 has, well, altogether there are 4 topics. So theta1 is like 0.3, 0.4, 0.2, and what's the remaining? 0.1, yeah? So if I actually want to draw Z1, say 5 out of, that distribution, all I need to do is to multinomial where theta1 is used as a parameter, right? So I will draw using this weight to actually draw. And I knew that Z, ZDN could actually belong to 1 to 4, okay? Because there are only 4 different topics. It only has got probability of generating either first topic, second topic, third topic, fourth topic. Okay. Okay, who didn't get it? I don't want to explain it again because that's important. Because only if you get it, we can talk about the graphical. All right, so now nobody answers. I'm gonna ask next question. So knowing that we already know ZDN, okay? We know that. We don't know, maybe it's like 4, something like that. Where do you think the probability of WDN is? By looking at this graphic model. So what's the probability of WDN? And of course, it's conditioning on a lot of other things. But if you look at the graphical model, what does it condition on? It only conditions on ZDN, right? That's where, you see, this is where the probabilistic graphical model helps you. So it conditions on this. There's one arrow goes in here. There's also another arrow goes in here. So it's also growing another set of arrows. That's all your betas, P to beta, bk, okay? So, and how do you define this probability? Remember, beta k are the distribution of words for a topic, right? So you have 4 topics, every topic has different distribution of words. And ZDN is which topic that have generated my word WDN. Okay, so my question is, what's the probability of WDN? Anyone have an answer? Or what's the parameter? So multinomial distribution must input a probability as its parameter. Right. So which one? Let me give you a hint. So remember, we have talked about this thing before, right? The Gaussian mixture model case. The Gaussian mixture model case, right? Knowing Z, which index has distributed from that. So you knowing which Gaussian has generated that. So remember, we say P of Xi, all right? Conditioning on Zi and also the parameters, like let's say mu I then, right? And what did I say about the probability? It's a Gaussian distribution of what? mu zi, yeah? Okay, let's look at the same story here. Very similar. Very similar, exactly, almost the same. Can you tell me? Firstly, you need to deciding what distribution is. It's a multinomial distribution, right? Because that is a word. A word is in basically, by the way, this is something that you will know. In here, the word has no representation, it's just an index. Like the first word, the second word, the third word, fourth word. Okay, it's just an index. So it's a multinomial distribution of what? What's the parameter? So definitely we try to model WDN, right? So I'll put a comma here. And what's the parameter of this multinomial distribution? I mean, just draw some analogy to that. We have set of views and we got a set of betas. I shouldn't use the same, not, I should use like beta k. I'll make these two things even look similar. I'm just going to call them beta k. Just draw some analogy to it. Yes, thank you. So it's beta z d n. That's it. That's how easy it is to model. So do people get it? I mean, that's the last model I'm going to show you. The purpose of today's class is to show you what the probabilistic graphic model. But we can't talk about probabilistic graphic model without actually showing you a real model, right? Otherwise, it just talk about like A to B and it's kind of boring. So we have to talk about that using a real model. But you actually get that. Okay. I think we will talk about this thing, next week as well. So by the way, before we finish, so once we talk about the model, we obviously did not talk about the inference part. So once you sort of get, once you actually are reasonably okay with probabilistic graphic model, we will be spending time to talk about how do you perform posterior inference, okay? Especially variational inference and also MCMC, finite column Markov chain, which actually try to representing the posterior distribution in some ways, okay? Which you can actually make use of it. I'll just, in the last 2 minutes, I'll just tell you how significant this particular model is, the one that I just described here. This latent delay shield allocation, I think, has been cited more than, I don't know, 20,000 times, something like that. It's actually very, very popular. Does anyone know a researcher named Fei Li from Stanford University in computer vision? He actually teaches the course in computer vision, which you can actually watch on Stanford's website. Her thesis was actually, I'm not sure whether it's the thesis or not, but I mean, one of the papers that made her super famous is essentially just using the LDA, but in terms of the visual stuff. So she created something called the visual bag of words. And it's essentially just the LDA, but applied to images. So, I mean, that LDA stuff is actually very significant. It actually brings up a lot of surprise learning of things. Okay, so enough said about this. Please have a look at please do some revision as well. And also please do spend the rest of the week finishing up your homework 1. And, so what I will do is watch out for my email. I will run another, consultation before the homework due. And I will do some recollection of the things that, or the questions that people ask me during consultation. I will compile them in an email. I will send it to you guys as well. Okay, great. So I will see you guys next Monday.